We're now at section 15.2, Coulomb's law. This is a very, very important section. You'll use this kind of like you use the gravitational, we use the gravitational formula to calculate the gravitational attraction between two particles, two objects. This is, Coulomb's law is equivalent in that you can calculate the force between two charges, either a repulsive force from two like charges or an attractive force from two unlike charges. Okay, this is Coulomb's law. In 1785, Charles Coulomb, who lived from 1736 to 1806, experimentally established the fundamental law of electric force between two stationary charged particles. An electric force has these properties. Number one, it is directed along a line joining the two particles and is inversely proportional to the square of the separation distance between them. Number two, it is proportional to the product of the magnitudes of the charges of the two particles. Number three, it is attractive if the charges are of opposite sign and repulsive if the charges have the same sign. From these observations, Coulomb proposed the mathematical form of the electric force between two charges shown here. There it is. Where Q1 and Q2 are charges separated by a distance r, and K sub E is a constant called the Coulomb constant. This equation is known as Coulomb's law and applies exactly only to point charges and to spherical distributions of charges, in which case r is the distance between the two centers of charge. Electric forces between unmoving charges are called electrostatic forces. Moving charges also create magnetic fields, which we will look at in a future topic. The value of the Coulomb constant depends on the choice of units. The SI unit of charge is the Coulomb, capital C. From experiment, we know that the Coulomb constant in SI units has the value given here. For this class, we will use either 2 or 3 significant digits as usual. So the Coulomb's constant is 8.98. You can use 8.99. You can use 9.0. That would probably work too and introduce a little error. 8.99 times 10 to the 9th newtons per meter squared per coulomb squared. Okay, here's some. This table lists the charges and masses of the proton, neutron, and electron. As you can see, the charge on the proton has a magnitude of E equals 1.6 times 10 to the minus 19 coulombs. That means it would take 1 over E to the 1 over 6.3 times 10 to the 18 protons to create a total charge of plus 1 coulomb. 1 coulomb is a very large amount of charge. In typical electrostatic experiments in which rubber or a glass rod is charged by friction, there is a net charge on the order of a microcoulomb. Only a very small fraction of the total available charge is transferred between the rod and the rubbing material. Okay, here's a figure of 2 point charges, 2 like charges and 2 unlike charges. When using Coulomb's force law, remember that force is a vector quantity and must be treated accordingly. The figure on the left shows the electric force of repulsion between 2 positively charged particles. Like other forces, electric forces obey Newton's third law. So that means the forces F12 and F21 are equal in magnitude but opposite in direction. Note that the notation F12 denotes the force exerted by particle 1 on particle 2. Likewise, F21 is the force exerted by particle 2 on particle 1. From Newton's third law, F12 and F21 are always equal, regardless of whether Q1 and Q2 have the same magnitude. The Coulomb force is similar to the gravitational force. Both act at a distance without direct contact. Both are inversely proportional to the distance squared, with the force directed along a line connecting the two bodies. The mathematical form is the same, with the masses m1 and m2 in Newton's law replaced by q1 and q2 in Coulomb's law, and with Newton's constant g replaced by Coulomb's constant k sub e. There are two important differences. Number one, electric forces can be either attractive or repulsive. The gravitational forces are always attractive. And number two, the electric force between charged elementary particles is far stronger than the gravitational force between the same particles. Okay, next we're going to discuss electric fields, but we'll stop this portion here.